Hi pre-calculus students, it's Miss Culver. My video today is on your exercise, multiplying and dividing complex numbers in polar form. First of all, I want to say some of you have been having trouble with inputting the correct answer into this exercise. I get it. Treasure was good enough to say if you only use parentheses, it works. But no worries if you actually know what you're doing on this exercise, because the math is actually pretty easy, just multiplying and adding, but you can't get Khan to accept your answer. So what I'm doing today is take a look. There is a ton on the board here. Please understand that you do not need to take notes on this. The reason why I have this information on the board is Dylan asked why. Why? Let's look at this first section here. How come when you have a complex number, they call complex number z, and you have a first complex number z1, that it equals r1 times cosine of theta 1 plus I sine theta 1. And let's say you have a second complex number z2, so we're looking at the top in blue here. We would call that r2 times cosine of theta 2 plus I sine theta 2r. And by the way, with those 2's at the bottom, those are actually, and the 1's at the bottom, those are called sub 1, sub 2. So the math is easy. These are complex numbers in polar form. And it turns out, let's look in red, if you multiply these numbers together, you simply multiply, whoops, hold on, gotta fix. It's just me today, folks, so I don't have anyone videoing me. Here we go. There we go. There we go. Did a little fixing. There we go. Back to red. That if you want to multiply the two complex numbers, it's just you multiply the two r's, and for the cosine and sine, you just add the two angles. And then if you want to divide the complex numbers, it is just you divide the r's, we'll talk about what those are, and you subtract the angle measures. Okay, so easy math. But number 2 in green, why? Why do we do this? If it's so easy to subtract, to multiply and divide complex numbers, when they look in standard form here, like a plus bi, why are we putting them in polar form? Here's the reason why. Because some very difficult high-level math with complex numbers in conic sections and vectors is made easier using the polar form of complex numbers. So this is actually for higher math. So I know what's happening here is when you multiply and divide these complex numbers in polar form, it's more difficult than if you have it in standard form. Like, why am I making it harder? But when you go to use powers of complex numbers, and when you do the trigonometric form of a complex number and you're rotating conic sections, or much later in math when you're using things called eigenvectors, polar forms of complex numbers are much easier. So here we go. Dylan Aleph wanted to know, well, why? Where does this come from? Again, this video is not meant to show you how to do this math here in red, z1 times z2 divided by z1 divided by z2, because it's easy to do. I'll show it at the end. It's just meant to show, why does all of this work? Where does it come from? So let's go to the middle. In the middle, there's a lot of information here that we would have learned over the course of a few days, quite a few, in pre-calc, and we would have said where it's coming from. We would have step by step over the days gone a little bit further. Let's look at number 3 in green. Where does this polar form of a complex number even come from? So when we look in blue here at z1 and z2, where does that even come from? Why is that there? Let's go back to 3a in black. We know the standard form of a complex number. There it is, a plus bi. B. Now, when you work with complex numbers, we like to graph them. And so we graph those on a complex plane. It has its own name. It's called an Argand plane. And what we do, going to get a little closer here again. I hope I do a good job. It's just me. What would be the x-axis is where the A goes. What would be the y-axis is where the B goes, the imaginary part of the number, right? And to graph a complex number, it's super easy. It's just if you had the number 3 plus 2i, the 3 just goes on the x-axis, which is now the a-axis, and you go up 2 on the imaginary axis, which was the y-axis. So it's just really the point 3, 2, but it's on the complex plane. Now this length right here, what we usually do is connect a complex number to the origin, and we call that length r. So we know how to find that. We've done the distance formula, right? Pythagorean theorem. On the Argand plane, this length is no longer called the distance formula or the hypotenuse, right? It is called the modulus. So r is the modulus. So when I come back up over here, that r1 and r2, those are called moduli. R is the modulus 1, r2 is the modulus 2. Okay, so nothing you don't already know on 3b here, just with different vocabulary because we have a different system. Now what I want you to know here is this relates to vectors also, which is why you're studying vectors in your Khan Academy Pre-Calc Recs for BC, right? Because vectors and complex numbers go together. If I simply put where this dot was an arrow on the end instead, it would be a vector. Okay, let's go down a little lower. So here's where it kind of pulls together. So notice if I made a right triangle in the graph above. So notice all I did was drop a vertical line to the a-axis, right? There it is, I dotted it. That, let's look in black here, that if I asked you what is cosine of theta, right? Here's adjacent, opposite, hypotenuse. If I asked you what was cosine of theta, you would tell me it's 3 over r. Notice if I multiply both sides of this equation by r, I get r cosine equals 3. Notice 3 is my a. Okay, let's go back to the picture. If I asked you what is sine of theta, you would tell me 2 over r. Right here it is. Sine of theta is 2 over r. Notice if I multiply both sides of that statement by r, I get r sine of theta is 2. Notice that, that's b, right? Take a look here. That's my b, that's my b. Okay, so here's what I now know. Here's where it all comes together at the bottom. So if a equals r cosine of theta and b equals r sine of theta, then that means right here in this complex number, I can put r cosine of theta for a and r sine of theta for b with the I. And that is the polar form of a complex number. Let's come on down. Z, which is a complex number, is r cosine of theta plus r sine of theta times I. Notice at the very bottom in the box with the exclamation points, all I did was I saw that r, which is the modulus, is a greatest common factor, and I pulled it out. And that is the polar form of a complex number. That's where it came from. All right, so the last question we're going to answer, number 4, I'm so excited when students want to know why. Oh boy, this is a mess. Is, so how come if you multiply one complex number by the other, you get the moduli multiplied together and you add the angles? Well, this proof comes from the sum and difference formulas for 2 angles. You learned it in Khan Pre-Calc Recs for AB. So you were doing trigonometric identities, remember that? You had double angles and you had cosine and sine of 2 angles being added and subtracted. So what I love about this is look at how much is pulled in, right? We have complex numbers, right? We have trig here. that writes these complex numbers in polar form. They are also related to vectors, right? And where does the proof come from? From the sum and difference of two angles being added or subtracted from trig that you probably felt, when would I ever need this? But the only way to get to the polar form of complex numbers and do math was to know those sum and difference formulas that you had. So of course, when you look, I don't expect you to really know what's going on here. I mean, look at all this, right? But I did write it out. So take a look though. Z1 times Z2, the top line there, all I did was multiply the two complex numbers together. Then all I did was do FOIL, first, outer, inner, last. Okay. When I did that, I just want you to see that what I came up with is a minus sign. And you'd be like, where did that come from? How can I possibly have a minus sign here when above, when I was foiling, everything was positive? Well, when you look here, see, when I FOILed out, the last thing I would have multiplied was I sine of theta 1 times I sine of theta 2. That would have been sine of theta 1 times sine of theta 2 times I squared, which is a negative 1. And that's where the negative came from. On the next line in blue, all I did was rearrange my terms. And when I did that, I found that I actually had the formulas for the sum of two angles being added for cosine and for sine. Okay? And of course, if I had the time in the room to do dividing the complex numbers, we would have seen division of the moduli and subtraction of the angles. So at the bottom, here's the easy math that Khan is asking you to do. So after proving all this, the polar form of a complex number, and seeing where it came from, it turns out the math is easy. If Z1 is 3 cosine of 30 degrees plus I sine of 30 degrees, and Z2 is 2 cosine 25 plus I sine of 25, to multiply, just multiply the moduli. 3 times 2 is 6, right here. And just add the angles. 30 plus 25 is 55. There we go. If you want to divide these two complex numbers, divide the moduli, 3 divided by 2, and subtract the angles. 30 minus 25 is 5. 30 minus 25 is 5. So again, the math is super easy, but here is where the math came from and why we can do it. I hope this helps. Have a great day.